Hello everyone, I'm a reporter from Taiwan. Today I'm going to report problem number 12.
Your name, please. Hello.
Your name.
It may be hard. Can you say by words? Can you say your name?
My name is Huang, and today I'm going to report problem number 12, Torsion Gyroscope. This is the outline of my report. First, I will introduce the problem statement, and later I will show the observation video of this phenomenon. And I have a preliminary research of this kind of motion, and later I have more experiment to investigate this phenomenon. And finally, I have a numerical solution in order to fulfill a task that I need to get the dynamics of the gyroscope. And finally, I will come to the conclusion. And this is the problem statement. So fasten the axis of a wheel to a vertical strand that has a certain torsional resistance. It's like this figure show. And twist the strand, and spin a wheel, and release it. What I'm going to do is investigate the dynamics of the systems. So according to the problem statement, there are two main points. First, we need to have a thread with torsional resistance, and later I will investigate the dynamics on the gyroscope. And this is the phenomenon observation. So as you can see, there is a gyroscope with a torsional thread, and as you can see, it will tilt and fly into a large angle and then reverse. And here you can see that we have a calibration tab in order to calibrate the angle of view to capture the video. And here we can see that there is a blue sheet which we can record the angular frequency, and it will also cause a little bit damping like the air drag, so that we can get a sound from the phone to get the actual angular frequency of our gyroscope. And here is qualitative experiments. So first, in the observation video, we can see that there are three different types of motion of this gyroscope. First is for the precession, which it will traces in the radius, and it just like this show. And second is for the nutation, the gyroscope will like this. And third is spin for the gyroscope. So here in our observation video, we can actually find out there is a criterion angle, which means the gyroscope tilt and fly at a maximum angle and then reverse. And so we define this angle like this, and we call it a criterion angle, which is a symbol of the torsion gyroscope. Like this video show, we can see that it has tilt and fly into a fixed angle. And here are the possible factors of the gyroscope, which the simple idea of how this phenomenon happens is because that the torsional resistance and the angular velocity will both towards the torque and make this phenomenon happen. And here are some preliminary results for torque and angular velocity. So as you can see in this graph, when we increase the torque of torsional torque and also angular velocity, we can have a bigger criterion angle. And I would like to talk about the experiments that I have done. First, we have a gyroscope, and we have thread which with torsional resistance, and we put the high-speed camera, and we put two different cameras in order to get a three-dimensional motion of the gyroscope. And the first camera to capture the XZ motion of a gyroscope, and the second camera to capture YZ motion of a gyroscope. And later we will merge the graph, and we can get a three-dimensional motion of the torsion gyroscope. It's like this figure show. And here we're going to talk about a numerical solution, because the problem statement told us we need to investigate the dynamics of a gyroscope. So here we want to discuss the numerical solution of the gyroscope. And in order to get a correct equation of motion, we set a body fixed frame of reference on the gyroscope. And first, I would like to talk about how can I set a body fixed frame. And first, we use the Euler angles to help us to set the frame of the gyroscope. And this is the simple idea of the Euler angle. First, you can look at this photo. The gyroscope has a precession which will run in this direction, and which is rotation angle is like this, which we call this theta. We'll call it phi in our theory model. And later it has a nutation which like this, and we call it the theta, which is this angle. And third is for spinning itself, the gyroscope will spin, and which is at this direction. And due to this three kind of motion is at a vertical direction, we set this friend in order to make us more easier at the mathematics to get the equation of motion of a torsion gyroscope. And so we get a rotating friend, which we call the omega friend on the gyroscope, which is rotating with the gyroscope. And because the friend is not an inertial friend, it is a rotating friend, so they exhibit some fixed force. And so first, the conservation of the angular momentum need to, torque balance need to like this. The external force torque plus the fixed force torque need to be 0. And here are some fixed force that we consider. First is the inertial force, because they are rotating friends, so we need to consider this. And second is for the centrifugal force. And the third is for the Coriolis force, because there may be their velocity, and force for the Euler force, because there are angular acceleration, so we need to consider Euler force. And here we calculate the torque of the fixed force. And first is the inertial force. Because we equivalent to acting on the center of mass of the inertial force, so there is no armor force, so there is no torque in this case. So we cancel it because there is no torque. And we will calculate the centrifugal force. And for the Coriolis force, because we said it's body fixed friend, which our friend is rotating, so there is no speed in the friend, because in the center of the gyroscope, because it is actually rotating, and because there is no velocity, there is no Coriolis force. So we cancel it. And force is for the Euler force, because there are angular acceleration, so we need to take the Euler force into consideration. So we mainly focus on the centrifugal force and the Euler force in our calculations. So first, we calculate the centrifugal force by the mathematical determinant, and we can calculate R cross F in order to get the centrifugal force. And after a calculation, we can get this equation of motion relevant to the moment of inertia and also the angular velocity. And second, we calculate the Euler force, because there's actually angular acceleration, which is this part, and we use R cross F and use the mathematics to calculate the torque from the Euler force, which will like this after the calculation. And so we combine this equation together, we finally get the equation of motion, and later we will run on simulation to see if our equation of motion is correct or not, to explain the dynamics of a torsion gyroscope. And so first we need some parameters in order to run our simulation. And first we need to get the torque of the torsional strap, which we assume that is the constant number divided by the length of strap and times the twisted theta. This is the angle theta. And here's how we gather the constant number in order to get the torque of the torsional strap. And after we get the torque of torsional strap, we can easily use the torque equals to the moment of inertia times angular acceleration to get the moment of inertia of a gyroscope, like this video show, and we can get this moment of inertia. And we get the spinning data, which is C, and which is the blue sheet give us the spinning data from experiments and insert it into our equation of motion to run the simulation. And this is our simulations look like. So as you can see, this is the torsion gyroscope. This is torsion strap, which was torsional resistance, and this is gyroscope. And as you can see, you have a precision and run a bigger angle. And here we want to give some comparison between our experimental data and our simulation result to see if our equation of motion could explain the dynamics of torsion gyroscope or not. And this is for the center of mass of the gyroscope. We can see that because it's like tracing on a circular motion, so there at the st direction you will like this result, and the simulation quite fit the experimental data pretty well. And for the y direction, because it's also like traces at a circular motion, so the result will like this, a little bit vibration. and the simulation also fit experimental data pretty well. And for the Z direction, because we actually collaborate on the view angle of view on the forward part and the back part, we didn't collaborate on the vertical direction. So the experimental data is a little bit different to the simulation, and there's a little bit tilt in the experimental data. And we comparison between the theta, which we call the notation in the reality, and our simulation. And as you can see, the simulation turns into be a little bit fat because we actually run on Excel for 1 billion data, so it will like this, and consider the arrow and like this, which also fit the experimental data. And the last is for the precision of the gyroscope, which means the gyroscope will traces at the angle, and we can see that phi angle simulation pretty fit with the experimental data. And finally, I will come to the conclusion. So first, there are two states of torsion gyroscope, which it will tilt and fly at the maximum angle, which we call it the criterion angle. And the second, we have preliminary research, we can see that when the torsional force becomes bigger, the criterion angle becomes bigger. And the initial angular velocity becomes bigger, the criterion angle will also be bigger, because that the torque causes this phenomenon. And here because the task of this problem is to investigate the dynamics of the gyroscope, so we give a numerical solution, which we use the concept of Euler angle in order to have easier calculation to solve a complicated rotating dynamics in 3-dimensional of the gyroscope. And we use the concept is principal axis and also the determinant to help us to solve this kind of complicated problem. And this is the dynamics, and this is the result. Thank you.
Did you vary the radius of wheel in any of your tests?
What do you mean?
Did you vary the radius of the gyroscope, sorry, in any of your tests?
I use the same gyroscope.
Same gyroscope,
yeah.
Yes.
And I test the moment of inertia.
Did you test altering the angular momentum or angular velocity of the gyro?
You mean I have tested different angular velocity of the gyroscope.
Yeah. How did you vary the torsion in your string that you used?
I've told at a presentation that I assume that the torsional stress is equal to yeah, I've tested constant number. Yeah,
have you considered the elasticity of the string?
I think that in the elasticity of a string is not really important in this kind of problem.
Okay. Did you test different weights of the gyro? Like, did you add weights to your gyro, or did you just keep it the same in all tests?
I use the same and keep it the same.
Does your theoretical model account for the torque induced by the weight of the gyro?
What do you mean? We consider the moment of inertia of the gyroscope.
Moment of inertia. Okay. Did you do tests considering the distance? So in the flying gyro, did you consider the distance from the starting point of the flying gyro, or did you just consider its tilt?
What do you mean? Because we can see that in the video, it will start to, not this video. You could just show the observation video. It will tilt and fly at an angle.
Yeah. Did you measure the distance from the origin that it flies at?
No, we didn't.
Okay.
Yeah.
How did you induce a constant spin velocity on the wheel?
Spin.
So how did you impart
I use a blue sheet to record the spin of the gyroscope.
Okay. Yeah, thanks. Thank you. Hello, my name is Campbell, and I'm going to be opposing torsion gyroscope. So I will first go over some positives of the theoretical work. So I thought that the numerical solution to the problem was very impressive, and I really thought that it demonstrated a really strong understanding of the dynamics acting. The consideration of forces from a fixed body rotating frame of reference was very good in that without setting this frame of reference, the directions of the different relative forces acting are changing. So I thought that was very well done. I thought there were some negatives though. I think he didn't account for the difference between the wheel tilt angle and the string angle, which I think is actually a very important factor. He didn't explain the directional reverse. I didn't understand the directional reversion in his presentation, and he did not qualitatively explain the change in the y component of angular momentum, of the initial spin angular momentum around the wheel axis. And there was little explanation of why the gyroscope begins to tilt. I think it would have been clearer if he put force diagrams in to demonstrate the direction in which the forces act. And he had little explanation of how the torsion in the string imparts torque. So he introduced torsion as a concept in his definition, but he didn't explain at all how that's transferred into torque and how torsion in the rope is propagated into torque. He had some positives in his experimental work. It fitted very well with his theoretical simulations, which was a good validation of his model. And he had clear videos and photos. But he did not vary a few relevant parameters, like differing the weight of the wheel, the length of the string, the radius of the gyroscope, the elasticity of the string, and he did not consider the distance from the starting point of the flying gyroscope, which I think, when you're investigating motion, as this problem states, he has done very little investigation on the motion of the gyroscope. So I think that was a real flaw in his presentation, is he did not consider the motion of the gyroscope in full detail. He only considered parts of the motion. And I think he was unclear when he talked about how he measured the angular frequency. So with that, I'd like to divide you up. So could you explain, you mentioned there's directional reverse, there's a directional reverse of the tilt and fly of the gyroscope. Could you explain how that happens, please?
So there's a thread with torsional resistance, right?
Yes.
And it will help the gyroscope to tilt and to spin, and it releases torsion. It releases torque by twisted angle release, right?
Yes.
And it will form another direction of twisted together, and so it will reverse because the.
So you're saying that the direction of the torque implied by the torsion in the rope will reverse once it gets goes past the equilibrium.
Yeah, it was initially twisted in one direction, and when it is released this torque, and it will twist it on the other direction, and then release another.
Yeah, I would agree with that.
Yeah,
Yes.
this is why the gyroscope will.
Okay, could you explain how the torsion in the rope imparts torque, please? So why does putting torsion in a rope create a torque?
Oh, because we could know that to show the visual page of the simple concepts. Okay, we can see that when the torsional torque is released, and by there's a force and R cross F, we can get a torque, which will help this.
Yeah, but how is that torque imparted? Why is there that force? Could you explain why the rope does impart that force? Because you haven't explained why the torsion will impart that force. I know there's a force imparted, I know there's a torque imparted, but I want you to explain why.
So what you mean is that why will the torsional strap give a torque to the gyroscope?
Yes.
Yeah, because actually the gyroscope is suspended on the strap.
Yes.
And when it is released, it's torque. When it is released,
Yes. Why is there a torque?
Because the twisted strap has a torque.
Okay, I would say that the reason that the torsion imparts a torque is because if you need a rope with some elasticity, and so as the fibers in the rope are stretched radially as they are winded around each other, this will create stretch in the rope, and due to this stretching, as they return to their original position because of their elasticity, they impart that force, which causes the rotation.
Or believe that is when you twist the strap, it's like you store an angular.
Yes, you store a sort of
released,
rotational elastic potential in the rope.
It's like you can tell me this is elastic potential. It's like like a potential of angular momentum and make it.
Yeah, exactly.
Yeah.
Could you explain what effect varying the elasticity of the rope would have on your gyroscope, please?
In my case, I didn't change the strap, the elasticity of the strap.
What effect do you think it would have, please?
It will influence torsion for sure.
So how would that influence the motion? What dynamic would that change, and how would that influence the motion?
As you can see about the numerical solution, and you can see that the torque that released from the strap will influence the precision of the gyroscope. If there is less torsional of the strap, it won't like tilt like away. It will just spinning like a pendulum. Yeah.
Could you explain how the weight of the wheel affects the precession rate, please?
The main point is
Could you draw a diagram,
the weight of wheel, but the moment of inertia of the wheel. Because I'm discussing the rotating of
yes, the precession around. So
yeah.
Do you think what effect do you think that would have on the precession? Do you think it would if you increase the weight of the wheel? Do you think that increases the precession or reduces the precession?
If you increases the moment of inertia of the wheel, it will decrease the precision.
Okay. So if we're considering a diagram of your gyroscope, could you please draw a diagram with the relevant? I want you to draw the relevant torques acting on the wheel, please. So can you draw a free body diagram of the wheel, and can you indicate the forces and torques acting, please?
So there's a. Sorry, I don't know how to draw.
Yeah, that's fine. Yeah.
Strap. This is Jumbo, and it has rotation, which have angular velocity,
Yeah.
and when it is released, torsional resistance, it will like this.
Okay. So
it will this time will spin in a less direction, and this will spin in a less
and
direction.
once in the tilting frame, so you mentioned the tilting of the gyroscope.
Yeah.
Could you draw the torques acting and the angular momentum while it's tilting?
While it's tilting, okay.
Yeah.
So maybe like this. This is gyroscope, and it's still spinning.
Yes.
And the strap direction will still have a torque. So the combination like this.
Yes. So I would say that you need to actually draw your vector to see the vector addition that you've drawn there. You need to actually draw in the vectors. So you've shown the torque as that, but the torque due to the torsion in the rote is represented like that, and the torque due to that precession using the right hand rule. It's going to be you put your fingers in the radius of the wheel, curl them in the direction of the force, thumb is in the direction of the force. Yeah. So the angular momentum is in that direction. So in this case, yes, I agree. It would cause an increase, and that's why it tilts.
Precession?
Yes. But I think you missed the torque here due to so the weight. Consider the center of mass of the wheel as this point here. So that is the weight of the wheel.
Yeah.
Then consider the distance from the rotating frame that the weight is at. So
actually,
this distance here. Did you consider
actually
that?
because we set a body fixed frame, so the frame is on the gyroscope. So the inertia force didn't cause a torque, since inertia force is equivalent to acting on the center of mass.
So yes, because you set that rotational frame.
Yeah.
Okay, yeah. I think varying the weight of the wheel would have been relevant. Do you what effect would this have on the motion of the wheel?
Just as I talked about, the moment of inertia will influence the precision of the gyroscope.
So the precision will increase.
If you have bigger moment of inertia, the precision will decrease.
Okay. So if you don't consider it in a rotational frame, and you consider simply the torque imparted by the weight force as an additional torque acting, so you consider this weight torque at that distance is going to impart a additional torque directly into the page here.
Sorry, you are considering the lab frame or rotational frame?
Just a still, just a yeah. And then if you look at the influence of the weight, I think it will influence the precession. So if you look at the weight and the distance away, that torque is going to be equal to the weight times the distance away. So when you integrate that in respect to time to get the change in angular momentum due to the weight of the wheel,
yeah,
I think once you add those vectors, it would actually influence.
Yeah, I agree. The weight of the wheel will influence the
precession
in the laboratory of view. But we set a body fixed frame, so it will cancel out.
So you neglected that.
Yeah.
Okay. So when you consider the changing the initial angular momenta of the wheel.
Angular velocity.
Yeah, angular velocity of the wheel. How did this influence the tilt angle?
If you have a bigger angular velocity of a wheel, you will have bigger tilt angle. Because this actually becomes bigger, and you will have bigger tilt angle.
See, I disagree because when you add, so you just consider these vectors here.
If I fix the torsional stress, I just change the angular velocity of the wheel, certainly the torque will become bigger and make the tilt angle become bigger.
So I disagree because say I label that L1, and then if you integrate that torque in respect to time, I label that L2. If I consider adding these vectors, so I have this vector here, that vector there, so the resulting vector is in that direction.
Yeah.
You take that as the angle of theta, so that is the angle of elevation.
But it's an initial state. Actually, it is at a first state, and when it's tilting, and it will like this, and combination will like this.
Yes, so
it will.
The directions of these stay the same in reference to each other, but they rotate up.
Yeah.
I agree, but if you just take consider it in a single instant.
Yeah.
The magnitude, the direction of this, the angle of theta is inversely proportional to the weight torque.
What I mean is that the angular velocity for wheel it become bigger, the
yeah,
tilt will become slightly, but in the end it will have bigger.
Sorry, I misspoke. Sorry. If you increase the magnitude of this vector, the angle of tilt will actually sorry. The angle of tilt will actually reduce because if you take the tan of that angle to find the resulting, it will actually reduce. So I think the angle of tilt is actually inversely proportional to the initial angular velocity.
But based on our experiment.
Yeah, I know you looked at the rotating frame of reference and
what happened?
Yeah. Okay. Why did you not, so when you consider the motion of the wheel, why did you not consider the distance that it travelled, so the fly distance, the distance from the starting point?
What is it important?
So the question is,
we want to investigate the dynamics of a gyroscope
and the effect on motion, right? So if you consider the motion of the gyro while it's in flight, so this is, say the gyro is in flight at this point, right?
Yeah.
And that's the gyro there, just for simplification.
Yeah.
Why did you not consider its motion over this frame? Because that is definite motion. And why would you not consider the effect on
maybe
dynamics?
I think I a little bit misunderstand your question.
Okay.
And in the comparison result, you can see that we are XT graph and we are YT graph, which XT graph is next direction. So we actually compare.
Okay, yeah.
But
Sorry, the clarification.
We not compare with the first point, but we can know the trajectories of the gyroscope.
The trajectory.
Yeah.
Yes. Okay. Can you explain how you measured the angular frequency in your experiment?
Actually, I have a blue sheet, and when it is is spinning, it will hit the gimbal of the gyroscope, and I put the foam under it and
frequency.
recreate. Yeah.
Why did you not consider the difference between the wheel angle and the tilt angle? So, for example, in your tilting frame,
There is no time for answer.
Thank you.
Thank you.
Okay. In summary, I think that their presentation was very strong, and I agreed a lot with this numerical theory by setting a rotationary frame of reference. I think there was a bit of confusion about the effect of various vectors on it, but I think by setting a rotationary frame of reference, you limit your conclusions, and I think he did not fully consider the motion, and I think it would have been more productive to answering the question if he considered the motion more fully and more in detail. But I thought his numerical solution was very strong, and I thought he didn't know how the torsion in the rope imparted a torque, so I think that was the main weak point, is not knowing how the torsion in the rope actually imparted part of the torque, which is a vital part of the question. Thank you.
Thank you. Maybe yours, please.
Good afternoon, everyone. My name is Robert. I'm the reviewer of Brazilian I'd like to make some questions to the reporter first. Okay. If you increase the torsion constant, the period of precession oscillation increases or decreases?
What?
If you increase the torsion constant, the period of
Torsion constant?
Yeah, the torsion constant. The wire.
You mean increase the torque?
Yes, it increases the torque.
The precession will become bigger.
Percent. What do you mean with bigger?
You have bigger tilt angle.
Okay, let's move on. If you increase the initial angular velocity of the period, if you increase the initial angular velocity of the spin, the period of precession increases or decreases?
Increases.
What about?
Could you please
Okay, if you increase the initial angular velocity of the spin of the torsion gyroscope, the period of precession increases or decreases?
Increases because the magnitude increased.
Okay, thank you very much. And how many times did you twist the thread?
You mean the angle, tilting angle?
Yes, yes. How many
Two
times?
turns.
Two times.
Yeah.
Okay, and you use Hooke's law for torsion torque approach. Okay, did you think that?
Hooke's law?
Yeah, for angle Hooke's law.
Yeah. Yeah.
Okay, did you think it's valid?
Yeah, it's
I
valid.
think it's valid. What about your opinion about this?
So using the Hooke's law to calculate the torsion, I don't think it's completely valid because he does not consider the elasticity completely.
Okay, and which torques are acting on the system? Reporter, please.
Please speak louder.
Which torques are acting on the system? Could you
Which
use-
torque is the torsional torque and also the torque caused by the angular velocity.
Okay, and what about your?
So the initial spin angular velocity around the wheel axis, the torque due to the torsion, and the torque due to the weight of the wheel as it's displaced once it begins to tilt.
Okay, and to the reporter, is friction relevant in motion of torsion gyroscope?
Friction, you mean air friction?
No, the friction in the wheel axis.
In the wheel axis,
Yes,
is not,
of the speed.
I think that is not really important in this
It's not
slide.
important. Did you investigate it?
We'll put it in our simulation. Yeah.
Okay. For the opponent, I want to repeat the same question. Is friction relevant in motion of torsion gyroscope?
I think it is because it means the magnitude of the spin angular momentum reduces over time.
Okay. And how did you measure the initial angular velocity?
Initially, I said I have a blue sheet, and when it's spinning, it will hit a gimbal, and I record the sound. I can get an angle.
So you record the sound, and by doing that, you could know the frequency of rotation.
Yeah.
Is that,
Yeah.
Do you think that this method is valid?
Yeah, I think it's valid.
Okay. I think that's it. Thank you very much.
Yes, go ahead.
Good afternoon. My name is Saito. I'm from Brazil, and I will present our review for the problem 12 torsion gyroscope. The problem asks us to pass index of a vertical thread that has a certain torsional resistance, which investigates the dynamics of this system. Okay. Here we have some strengths and weaknesses of the reporter. As strengths we listed here that the analysis goes through both torsion and gyroscoping motion in a stable manner, and in our opinion this is a positive point in his presentation. And all three kinds of motion of the gyroscope was addressed, and I also listed this as a positive point because this motion is governed by the motion of precession, rotation, and the spin. And also he used and explained other angles, and that, in my opinion, is the best method for symmetric gyroscope, which applies for his experimental conditions. And also he's presented some weaknesses, and here I listed some. Okay. He didn't explain the torsional torque values presented. He only said that there was the existence of torsion torque, but didn't explain for example, he didn't show the order of magnitude of the torsion constant he measured, or anyway. And yet, he also showed the absence of friction and damping terms in theoretical analysis. And I emphasize this because, in my opinion, the friction and damping terms in theoretical analysis makes difference in the motion of torsion gyroscope. Okay? And he also did not present a clear comparison between theory and experiment, which is, for example, in the absence and in the fitting parameters that in his graphs. And that's why I also listed as a negative point in his presentation. and he showed a narrow analysis in the rotation and in motion despite the stability of the system. So my suggestion for this review is that he should include damping term on the spin motion. Okay? To the opponent, here are some strengths and weaknesses again. He questioned the relevant parameters and experiment as well as initial conditions, and he provides qualitative analysis for the phenomena, and he engages the physical discussion. And also, unfortunately, he had some weaknesses as well. He didn't criticize noise in presented data. There are some vibrations in the torsion gyroscope that he didn't explain where these disturbances came from. And there was absence of questions related to the damping factors, which I said before is a pretty relevant parameter. Okay, and he didn't run through experimental analysis of reporter, which makes me conclude that it is incomplete analysis because experimental analysis is always important. So my suggestion to the opponent is to focus more on the experimental measurements as well. For example, the speed and the angles that the reporter has analyzed. Okay? And about the physics fight here, the topics discussed. They discussed the torsional torque and the acting torques in the system, and there was an extensive discussion around angular momentum of the system. So here have the questions that we wanted to emphasize. Is friction in the wheel axis in the system relevant? Well, the reporter said that is not relevant, and the opponent said yes, despite not questioning it. Our opinion is that it's pretty important because friction decreases the angular velocity of the wheel, and this wheel makes the precession angle very faster. Okay? And about the angular law applicability, the reporter said that it's possible. The opponent says that it's not valid. Our opinion is that it's valid only for small angles, and in this case, in the reporter's case, it was not applicable. Thank you very much. That's all.
Thank you. Here we are going to give a concluding remark, and for the elasticity of a thread will affect the torque of a thread, of course, because it is the concept of elasticity is like to store a torque in the thread and make a torque. And for the moment of inertia will affect the precession of the gyroscope, of course. And when the moment of inertia becomes bigger, the precession will become less obvious. And about reviewer mainly talks about we didn't consider damping in our numerical solution, but during our numerical solution, we actually record the real spinning of the gyroscope. So if there is damping, and we will record the damping. So we put it in the numerical solution, which the reporter do consider the damping in the numerical solution, which I think the reviewer misunderstand. And we actually set a body fixed frame, which on the gyroscope. So what the opponent talks about, the inertia force is effective acting on the center of mass, which did not have a torque in this kind of body fixed frame. And the moment of inertia is actually a tensor, so we can easily solve it in the laboratory frame. So that is why we use Euler angle in order to get the principal axis of the body fixed frame. And here I would like to play our simulation result again. As you can see, there is upper is the torsional thread, and it is gyroscope, and it is spinning, and it will have a precession. And that is, I think I actually investigated about the dynamics of a gyroscope, which I fulfilled the task of problem statement. And this is my concluding remarks. And thank you very much.
Thank you. Now questions for George.
Question for the reporter. You had a video where you have
Attention, please.
you had a video where you had the gyroscope going one direction and then reversing.
Yeah.
Where is it in your analysis?
In my analysis, I just analyzed the first round, and I didn't investigate about rotational front because the data was too big, and I can compute.
So it cannot be computed.
It can be computed, but my computer can force a lot of data. So I only consider the first round, and when it in reverse, I stop. So I calculate the criteria angle. Yeah.
Other questions? My question to the reviewer, you talk about the friction, but the friction has what it so yeah, the friction has some quantity. So there is no disagreement between you because everybody can imagine the different kind of friction.
Sorry.
The friction may be very small and may be very large. So the result will depend on time also.
But, yes.
So you may be, all of you may be right.
Sorry, I'm not understanding your...
The friction is
Sorry.
quantitative friction.
Yes, friction.
It may be very small, it may be very large. And
Yes.
the result will differ.
Yes, the result will be different.
Just one question maybe for you all of you. What do you think about the energy transformation from one to another? You have a motion and then it stops and it goes again, and then how do you will explain this with respect of energy?
It's like the torsional strand has stored energy, and when it is released the strand, and it will release the energy, and it will trace it at another direction, which will store energy again and come back.
We have potential energy associated with the torsion, torsion potential energy, and this energy is transformed in kinetic energy. For example, the precession and rotation motion of torsion gyroscope.
So you initially have the potential energy in the thread, and then once you release it, because of the angular momentum of the wheel, it goes past the point where there's no potential energy in the thread, and it goes potential energy in the opposite direction. So that's why it reverses direction.
Some other questions? No questions, please. Take your seats. Sign your protocols also. No, the first mark for the report. Please. 8, 6, 6, 5, and 5. The next one for the opponents. Please. 7, 6, 6, 6, 6. And the last one for the review. 8, 6, 7, 7, 7. I want the positive explanation. Now, for the report. The lowest mark, please, 5.
So I gave a low mark because from the videos, it's clear that there are a lot of rich phenomena. The richness of the phenomena is there, you observe it, but you neither qualitatively nor quantitatively show how they fit with your theory. So there's a very clear disconnect. So that's one thing. And I think you don't also tell us very clearly how you actually what you actually measure, okay, whether you actually fitted the experimental data to any parameters, or whether they were all measured. I thought that was very unclear. But the main thing is really that you did not look at all aspects of the phenomenon.
Yes? And your
I felt given that your presentation was almost entirely simulated and just limited like single test comparisons to like single runs of experiments rather than like averaged over a lot of things. And the fact that you, like I said, missed some of the, like that reversal that your videos clearly showed wasn't addressed. And also, as the opponent and reviewer pointed out, there was no explanation of the phenomenon, clearly, like the forces and torques that actually produced the phenomenon in the first place. They just launched into mathematics straight away, rather than describing it.
Yeah. And I want to say maybe about all this fight. I like it because it was a very great fundamental theoretical analysis. You made, I like it, you have two cameras and make the three-dimensional trajectories, and then analyze them and compare the experiment with the theory also it was shown, and all the main features of the, as it is written in the task, so investigate the motion of this gyroscope. So this was not needable to study the relevant parameters. It is not the task of this problem. And the same for example, for the reviewers. And I decrease a bit the grading for the opponent because you talk a lot of these parameters that they don't investigate them and so on. They make the main task of the problem. This is from my point of view. I was very glad to hear all this fighting. It was very it was a success, very active and resulting. So some minor remarks for the opponents. No, there is no great deviations, if anybody, and for the review also. Maybe somebody want to say in general about this fight. If you have questions to the jury, maybe the members of the team. So if you have not, we shall fix.